Yeah, we get 0 over 0. Okay, now, question was asked a couple times, what's this delta x thing? Is that 1 or 2 variables? What is that? Well, no, it counts as 1. What does delta mean in math?
It's a variable.
Change it. Yeah. It means when we're looking at, for example, a slope. For example, a slope. If we want to talk about the slope of a line, and later on in calculus, we'll talk about the slope of a curve. We can talk about that as being delta y over delta x, right? Change in y over change in x. So there's an example. In fact, what this is all sort of getting at here, this might look random, but it's not. This is something, this is what we're typically going to do with limits, is evaluate expressions like this. This comes right from, as we'll find later in the class, this is the limit definition of the derivative of a certain function. And we're going to use this, and I'm jumping ahead a little bit, but just so you kind of, when you see this, you'll think, okay, we'll talk about that a little bit. This is how we get at the concept of the slope of a curve, okay, the slope of a tangent line to a curve. But we'll get there later. Now all we're concerned about, we don't really know what it means at this point, but we know it's a limit, and we know that if we try to directly evaluate it, it comes up 0 over 0, which of course means more work. Well, what does the more work look like here? What do you suppose we do with this one? I don't know that this necessarily fits exactly into one of those categories of the indeterminate forms that we approach, but it's very similar to one if it's not exact. What do you think? What's your intuition tell you here? Okay, I mean, that's a possibility. We could multiply by the conjugate. It's going to start to get kind of ugly, though, isn't it? Because this quantity, x plus delta x cubed, it looks innocuous, but that really packs a punch. There's a lot going on there, right? If I expanded that out, there's a lot of stuff happening. As you're going to find, a lot of times when you see things that are sort of complicated abbreviations of larger things, oftentimes what's best to do is just to expand it out, just simplify and see what happens. You know, once we simplify, is there a way to do some cancellation that's going to be helpful to us? We know that there will be eventually, right? We know that something's going to cancel, but we just have to get to a point where we can see what that something is. So how about if we expand this? The only part that's really bad is this part. Okay, well, maybe we need a brief review of how do we expand out binomials like that. If I've got a binomial, meaning two terms added or subtracted, to a power, do you remember how to expand binomials? It's been a little while. We would have talked about this back in Algebra 2 a bit, but it's the pyramid. Yes, exactly, the pyramid. Very good. Yeah. Should we maybe do just a brief review of the pyramid? Okay. Okay. The pyramid, by the way. Well, we'll talk more about it here.
I knew it was you, but I messed it up.
Okay, the pyramid is called Pascal's triangle. Is that ringing a bell? And what Pascal's triangle does, anybody do you remember how to make the Pascal's triangle?
1, 1, 1, 2, 1.
Ah, okay, yes. Okay, so we're going to start with a 1, and then we're just going to kind of build a pyramid out of this. And then from now on, the slopes of the pyramid are always going to be 1s. But how do we get those interior points?
You add the 2 parts above it.
Yeah, there we go. So we're going to add the numbers above to the left and right. Always, we take the sum of those to produce the bottom number, right? So then down here, we won't go too far with this, but so this guy's going to be a what? 3. And then this guy's going to be a
4, 6.
Okay, and what these are, turns out, in Pascal's triangle, these are the coefficients of the terms in a binomial expansion, okay? So we're going to assign a letter, or excuse me, a number to each of these, each row in this pyramid. The first one is going to be the 0th row. So that's 0, that's 1, that's 2, 3, 4, etc. Charge of all. It's great. Okay, so anyway, so these are the powers that go with the binomial expansion. So for example, if I want to do something like a plus b cubed, then this is the row that expresses the coefficients of that expansion. Okay, so we know, but now what about the powers? Okay, we know that when we expand something like this out, do you remember the trick with the powers?
Yeah, A goes up as B goes down.
Or A goes down as B. Typically,
Yeah.
we could do it either way.
Let's do it. Yeah.
Other way around.
There we go.
But we're gonna the sum of the two exponents is always what?
3.
3. Good. So we're gonna start off with the first term is gonna be something times A cubed times B to the 0 plus something times A squared B to the 1 plus something A to the 1 B squared, and then I said leave myself enough room here, plus something A to the 0 B cubed. And what's anything to the 0 power other than 0? 1. Okay. And then here are the coefficients that get filled in, right? So this is going to be a 1, a 3, a 3, and a 1. And that's our trick. Okay, there is actually something called the binomial theorem, which for very large binomials, this would be quite cumbersome. And the binomial theorem gives you a formula for developing all of these coefficients. But honestly, for relatively small binomials, this is probably easier. Okay, so, I mean, and usually we don't oftentimes deal with binomials that are that big. I mean, if so, then we got to use the binomial theorem. And we'll look at that later. Okay, but so for our problem then, if we look at this guy, what's that going to be? So we've got the limit of what? What's going to be inside the bubble there? So what's our A in this case? Instead of A and B. A is X and B is delta X. And so what were those coefficients? Do you remember? 1, 3, 3, 1. Okay. So what's the first, what are the powers in the first term? X cubed and then delta X to the 0. Right, that's just 1. Plus 3 X squared delta X to the 1, right? Plus 3 X to the 1 delta X squared plus delta X cubed. Okay. Minus X cubed, all divided by delta X. Okay, that looks pretty messy, but what do you notice there? Yeah, the X cubes cancel. Okay, it always kind of works out, doesn't it? And it's not just by chance, it just has to. Turns out that, notice that in this limit, in math we would say the argument of the limit. The argument means kind of the dependent variable of what's the limit acting on. Well, the limit is acting on delta x's, right? We're taking the limit as the delta x's go to 0. What are the variables up here? Well, I guess you could argue that both x and delta x are variables, but insofar as the limit is concerned, the only variable is the delta x. That's the only thing that the limit is changing, right? From the limit's perspective, that x is constant. It's not really changing. Now, when we do this, notice that the only terms that don't have delta x's in them, the sort of the constant terms from the limit's perspective, cancel out. Sometimes in calculus we call those the naked terms. The terms that don't have a delta x in them, they go away. And so now all we're left with are terms with delta x's in the numerator. So what could I do then? if all those terms have at least one delta x. Factor it out, sure. I could factor out a delta x. Very good. Okay, and if I factor out a delta x in the top, what am I left with? Good. Plus delta x squared. Okay. All over delta x. Delta x goes to 0. Let me scoop that up for you a little bit. Okay, now what? Now, what did we always say? Remember when we started doing those evaluating the indeterminate forms, and we looked at some where we were able to factor? What always happened that allowed us to eventually take the limit and have it be determinate?
So one of the factors was on the denominator, so you could cancel.
Okay, we could cancel. We can cancel factors top and bottom, right? Now remember, we can only in algebra we can only cancel factors. We can't cancel terms, right? And I know with you guys, I probably don't need to say this, but I'm going to say it anyway. A lot of times people want to do things like this. And of course, that's not allowed, is it? Right? That doesn't work. That's no good. But we can do something like this, right? The difference being that in this case here, we're canceling factors. We're canceling, the a's are being multiplied. A is multiplied by b on the top, right? So it's a factor. Over here, because the a is being added to the b, it's a term and it's not a factor, so we can't cancel it, right? So then I can cancel those delta x's because this delta x is being multiplied by this other very large factor. I can cancel common factors. And it works out, doesn't it? Because the delta x, it turns out, the factor on the top and the bottom, that's what was causing the indeterminacy. That factor delta x, when delta x approaches 0, that's what's causing us to have the 0 on the top and the bottom, right? And so everything's good. When we cancel that out, now we can take our limit, we'd say in math, or evaluate the limit, right? Now what's going to happen? Once we've canceled out these factors and I evaluate the limit, what happens? Yeah, we just get a 3x squared, don't we? Because all of these other terms are going to go to 0 because they have delta x's in them, right? And so all we're left with is the 3x squared. Is it weird to have an x in our answer? Yeah, maybe it seems weird at first, but actually it's no big deal because we might have expected that. The limit, remember, was only acting on the delta x's. The delta x's were going to approach a constant value, and so they were going to turn into zeros. But the x's, the limit said nothing about the x's, didn't act on the x's. So we should expect that the x's would remain in our answer. Okay? Make sense? I think you had a couple like that on the assignment too, right? Should have. Yeah. Okay, what I want to plug in today, nothing major, I want to just talk about continuity just a little bit. And continuity is, we can make this very conceptual also. Continuity, think of it this way, when we're talking about the continuity of a function, here's a good kind of graphical way to visualize and maybe internalize this concept. Continuity of a function just means I can draw the function without picking my pen off the board. Okay, so a function is continuous on any interval where that can happen, where I can draw the function without picking my pen off the board. So then if we're talking about whether a function is continuous at a given point, there really are 3 criteria that we would have to meet for that function to be continuous at that point. There's only 3 reasons we would ever have to pick our pen off the board. One of them would be if the function were not defined at a given point. The function didn't exist there. So obviously the function needs to be defined if we're talking about the point C. If that's where we're scrutinizing the function and trying to determine if it is continuous at that point, obviously the function has to be defined there, right? So there's the first criterion. Second one would be that the limit, I guess I need to finish that, the limit as x approaches c exists. Now think about the three kinds of places where limits don't exist. What were those? What's one of them? Okay, vertical asymptote. Now obviously if there were a vertical asymptote, then we would have violated the first rule already, wouldn't we? Because the function couldn't exist there, right? So that one, limit wouldn't exist, taken care of. What was another one? Piecewise function. So if we have a break in the function, that would clearly be a case where I would have to pick my pen off the board, right? To bridge that gap in the function. And then the third one? Okay, and this is a little harder one to see, but if I had that weird oscillating behavior, do you see that if I were to try to somehow draw the function and it oscillated infinitely, even if I would need an infinite amount of ink in my pen, right? And furthermore, I need an infinite amount of time to make all those infinite wiggles, right? And so I guess you could sort of almost think of it this way. At some point, I'm just going to get exasperated and give up and take my pen off the board because I can't ever get where I want to go. So that one's a little harder to pin down to the pen analogy, but that's also that weird case that you don't see very often. And clearly, it fits the mathematical criterion that the limit doesn't exist there, right? And then the third possibility, or the third criterion, is that the limit has to actually equal the value of the function. Okay? Now let's look at some cases here where the function doesn't exist clearly, and I want you to tell me which of these is violated. Okay, which of these three rules is violated? How about this one? So here's our function f. So we'll call this point C. Which of those three criteria for continuity do I not meet this time? The first one, yeah. There's a hole in the function. F of C is undefined, right? Or does not exist. Okay? How about, I'll draw this one in red, same axes. Oops. Pretty obvious which one that is, right? We'll call that function G, how about it? Which one on there? Okay, limit doesn't exist, right? So this would be the limit of g of x as x approaches c. Does not exist. And last one, I better get another and redraw the axes. How about this guy? What about that one? Does it pass the first test? Yeah, the function is defined, isn't it? Right? So if this is c, what's the value of f of c? Is it here? Oh, it's right here, isn't it?
Yeah.
That's f of c. Thank you. Okay. And is the limit defined? Does the limit exist?
Yeah.
Where's the value of the limit?
It's on the line.
Okay, so it's going to be right there, isn't it? Right. That's L, and we'll say that the limit of f of x as x approaches c will define as L. So what's the problem then?
The function and the limit are the same.
Yeah, function and the limit don't coincide. So this violates the third rule. The value of the limit doesn't equal the value of the function, and that's why I got to pick my pen off the board. Okay, good. So those are our three criteria for point continuity. Now, all we have to do to extend this to continuity on an open interval. Now, open, does that mean I'm including the endpoints or not? What do you think? It's an open interval. You may have never heard that. Okay, an open interval looks like this. So maybe this answers your question. Here's an example of an open interval. So I'll make it bigger. Are the endpoints included? A and B? No, they're not. So what this says, if we were to turn this into inequality notation, this is saying all values of x where x is greater than a and less than b. We don't have the squared off brackets, right? So therefore we're not including the endpoints. Okay? So if we want to extend this definition to an open interval, we would say that a function is continuous on an open interval just if the point continuity is satisfied for every point on that interval. Okay? So if we're looking at the open interval from A to B, as long as for every point on that interval, these three things are true, then we've defined that open interval as being continuous. In other words, I know I can draw the entire interval without picking my pen off the board. Okay? And then, of course, we could say that if the open interval extends all the way out from negative infinity to positive infinity, then that's everything, right? We'd say that the function is everywhere continuous. All real numbers are included. Okay, but then and that probably all looks pretty good. The only real dilemma here, though, is how do we deal with the closed interval, right? So here's our open interval. We're going to go from A up to B. I can draw it from between the endpoints, but I can't draw it at the endpoints, right? And why can't I include the endpoints, do you suppose? Which of those three criteria is having trouble with the endpoints? I could fill in the dots on there. Would the function be defined at the endpoints if I did that? Sure, check. That works, whoops. That works great. Checks it off. What about the second one? What was at this point, our only definition of a limit, remember, is sort of our ant definition. And what did we say about the ant definition?
Approach from both sides.
Yeah, we got to be able to approach from both sides. Aha. There's the problem, isn't it? I can't approach the endpoints from both sides because the ant can't walk on anything. For example, if I'm looking at the left endpoint, where's the ant going to walk from the left to get there? He's got nothing to stand on, right? And so that's what's messing us up. It's this existence of the limit. So if we're gonna somehow be able to define continuity on a closed interval, we've got to tweak something here a little bit. Anybody have an idea how maybe we could do that? We're going to have to change the game a little bit. Obviously, this is the part of the game that's going to have to be changed. Anybody want to hazard a guess as to how we might have to do that? What do you think? Clearly, we're going to have to maybe define some slightly different kind of limit at the ends, right? We can't have a normal limit there. Any suggestions? What could we do to that limit that would maybe allow us to fill in that endpoint? What part of it could we never hope to meet of our ant definition? Tommy said it. We can't approach from the left, obviously, right? So maybe we could instead relax the restrictions on that a little bit and say, well, why don't we define a special limit that we can only approach from one side? But does that make sense? So for example, on the left endpoint, we could only approach it from which direction? The right. And for the right endpoint, if we want to fill that in, we could only approach that from the left, right? And then if we were able to do that, now we'd be in good shape, couldn't we? Because we already knew that we could fill in those endpoints and not violate the first criterion. It was that second one that we needed to be careful about. And once we've taken care of those two, as long as they're at the same point, the limit and the function are at the same point, we automatically meet that third criterion, right? So the way we do this then is this weird kind of special limit that we need for defining continuity on a closed interval called a one-sided limit. And it is exactly what it says, and it's no more complicated than that. A one-sided limit, we would say this. We could say that the limit of f of x as x approaches c, what do you suppose that means? That plus sign. From which direction? From the right, right? If we think about the real number line, this is where numbers get greater, right? That's the positive direction, and that's the negative direction. So we're going to approach C from the positive direction, from the right. Okay? Okay. So there's a one-sided limit. We would say that's a limit from the right. Okay? So there's our limit from the right, or one-sided limit, I should say, one-sided limit from the right. How do you suppose we say a one-sided limit from the left? Yeah, same thing, right? We'd say the limit of the function as x approaches c, but this time we've got to put a minus sign up there. And now we're approaching from the negative direction, right? Okay, and then the only thing we've got to do, if we want to extend our limit on an open interval to be a limit on a closed interval, is we would say that it looks exactly like, where is that, right? This, there, right there, yeah. We'd say that on the open interval, so between the endpoints, it acts just like a normal old continuity issue on an open interval, but then at the endpoints themselves, we're going to relax this a little bit and say that the limit there only has to be one-sided. Okay, so in the language of the book, and I want to get this exactly the way the book does it, here's what they say. Say two important things I want to draw your attention to. They say, first of all, we can tighten down our description of what a limit actually is. We'd say that let f be a function and C and L are real numbers. Okay, if all that's true, then we could say we've always said the limit of f of x as x approaches c equals L is true. Remember what that means? If and only if. Okay, so all these things have to be met. That's true if and only if the limit of f of x as x approaches c from the left equals what? The function, the limit of f of x as x approaches c, we could say is L, if and only if the limit of x as x approaches c from the left. So the ant coming from the left anticipates what answer? L, right? And we're not saying anything new, we're just restating it maybe with a little better terminology. The limit of f of x as x approaches c from the right equals L. So what did we just say? Well, nothing we didn't already say, but now we just made it mathematical instead of sort of ant-like, right? Now, instead of just saying the ant has to approach the same value from both sides, this is how we could mathematically say that, right? That the limit from the left equals the limit from the right. Okay, nothing new, just a way to say it. Okay, and then how would we extend this to our closed interval definition of continuity? Okay, we could say f is continuous on the closed interval from A to B if continuous on the open interval, the way we've described it. So for all values of C that are captured between A and B, for every point on this open interval, we meet those three criteria we talked about. And what else? How do we deal with the endpoints? What has to happen at the endpoints? We go back and look at our list. Yeah, it has to be defined. And we have to have a one-sided limit at the endpoints, right, that exists. And furthermore, they have to equal each other. But we can make this a little simpler. In a way, doesn't the third criterion really assume the first two? If the limit of the function has to equal the value of the function, then isn't that saying, well, in order for that to be true, obviously the function has to be defined and the limit has to exist if they're going to be equal to each other, right? So we could really wrap them all up into this nice third criterion if we want to, and say something like this. The limit of f of x as x approaches a from, if a is the left endpoint, from which direction do we have to approach it? From the right. How do we say that? What do I need to put here? Plus, good. Must equal f of a, right? So the one-sided limit from the right at the left endpoint equals the value of the function at the left endpoint, right? And what would we say for the right endpoint? The limit of the function as x approaches what? Okay, so the right endpoint is b, right? As we approach b from the left, must equal what? F of b. Okay, does that make sense? And this is in one of these nice, in your textbook, those nice blue boxes that give you all the key information. There it is. Okay, let's maybe, how much time we got? Let's say 42. Oh, we're about out. Okay, we'll maybe take a look at an example tomorrow, and then we'll go down and work on this stuff a little bit. How's the homework coming? I didn't look this morning. I haven't had a chance to look yet. I guess specifically I'm asking about the calculus stuff. Pre-calculus review, we'll look at that stuff as we get a chance. But how's the 1.3 assignment coming? Are we progressing on that okay?
Yeah.
Okay. Yeah.
So the continuous, when you had negative infinity,
Uh-huh.
brackets, how
Okay.
would that be different than oscillating behavior? Because you'd never be able to.
Okay, good question. So the question comes up, how can we define a function as being continuous everywhere? Because I'm going from negative infinity to positive infinity. Obviously, we can't. I couldn't draw that whole function because it's going forever. But what it means is that if I were to draw it, I could go arbitrarily far to the left or the right without ever having to pick my pen. Does that make sense?
But wouldn't the same be true for oscillating behavior?
Well, sure, but with oscillating behavior, it's a different story. With oscillating behavior, if I'm moving from left to right across the function, I'm going to hit a point where I can see a point where I can draw forever but never get to that point. With the other case where I'm looking at everywhere continuous behavior on a function, that's not the case. Then, although I could never draw the whole function, as I move along the function and draw, I can go arbitrarily far, right? And if I want to spend more time, I can always go further to the left or further to the right. There's never an impediment to my going there. Does that make sense?
Yeah.
Okay. It's a subtle difference, but it's different.
Yeah, I get what you mean.
Okay. All right.